Now let's see the equation behind spam filters, medical AI, and predictions. Okay, it is such a popular equation, and you'll find out just now. So the equation behind spam filters, medical AI, and predictions is simply the Bayes theorem. And so then we consider Bayes theorem and classification systems. So Bayes theorem is one of the most important concepts in probability, in statistics, in machine learning, in artificial intelligence, in medicine, in finance, and decision science. So it provides a mathematical framework for updating the probability of an event whenever new evidence becomes available. So many modern intelligence systems rely on Bayesian reasoning, including email spam filters, medical diagnosis systems, fraud detection, face recognition, recommendation systems, weather forecasting, search engines, and self-driving vehicles. So whenever a system receives new information and updates its prediction, it is simply performing Bayesian inference. So Bayesian inference is all about having to update your what you know when you have new evidence. So our learning objectives, after completing this lesson, you should be able to explain conditional probability, and that is the basis of Bayes' theorem in the first place. And afterwards, you'll be able to state the Bayes' theorem. Then you interpret the meaning of prior, likelihood. Prior knowledge, that's what prior is like. Likelihood, that's the likelihood of something happening. Evidence, that's new evidence you have. And posterior, that is you updating your state of knowledge. So you have a prior knowledge and there's a likelihood of something happening, and then you have an evidence to support it or not, and then you update your knowledge, and that is the posterior, like that. So solve Bayesian probability problems. Then you apply Bayes' theorem to real-world situations and implement Bayes' theorem using Python, as you're going to see, and then understand how Bayesian classifiers work. So let's go. So what's the motivation to start with? Suppose you receive an email with the following subject: win money now. You might suspect it as spam, right? And there's every likelihood it might be spam, because sometimes if it is too good to be true, it is actually not true. Okay. So however, suppose you observe additional evidence, like you see many capital letters, and you see multiple exclamation marks, and you see suspicious hyperlinks, and it's coming from an unknown sender. In that way, each new piece of evidence increases your confidence that the email is spam. So a very good example I like to give is, you have a group of three friends, right? When you see one of the friends around, you're so let's say you have friends A, B, and C. When you see friend A, you have there's a chance, a possibility of friend C being around. But then when you see A is there, B is also there, then the chances that C will be there is higher than when only A was there, right? So that is evidence. So each new piece of evidence increases your confidence that the email is actually spam. So this process of updating beliefs using evidence is precisely what Bayes' theorem describes. So Bayes' theorem tells you that situation that, okay, friend C is most like possibly around when you see friend A somewhere, and then so the chances of friend C being around is even higher when you see both friends A and B around. So this process of updating beliefs using evidence is precisely what Bayes' theorem describes. Just like you would most likely see that a mail is spam if it has many capital letters here, it has multiple exclamation marks. So it's trying to push you, or it has suspicious hyperlinks and the sender is unknown. And then we go on to the review of conditional probability. By the way, I have a probability playlist on this channel. So in case you need to know more about probability, so there I dealt with probability, and I think there's a whole video, I think, dedicated to conditional probability. So conditional probability measures the probability that an event occurs given that another event has already occurred. So something like, what is the probability that that a student graduates from high school, given that he lives with both parents? Or what is probability that somebody graduates high school, given that they are raised by a single parent? Something like that. So it is written as probability A given B. So this line you have is like given B, where A is the event of interest. What's the probability that the event of interest is happening, given that the observed evidence has had already happened? For example, What's the probability? So A means student passes an examination, and B means student studied. Then yeah, probability A given B means the probability that the student passes the exam given that the student actually studied. What is the probability of that? That is conditional probability. Now, then that takes us to Bayes' theorem, because in Bayes' theorem you have conditional probabilities. In fact, what you're actually looking for a conditional probability. Bayes' theorem simply states that they are looking for the probability that A happens given that B already happened is equal to probability that B has happened given that A already happened. I mean, it's equal to probability that B happens given that A had happened, multiplied by probability of A, multiplied all over the probability of B. So here, the probability that A happens is called the prior probability, more like the prior knowledge you had. The probability that B happens given that A had happened is the likelihood that you have right here. And probability that B happens is the evidence. And then the result you get is the posterior probability. So it's more like an update to your knowledge given the prior, the likelihood, and the evidence. Now, so we go on to talk about understanding the components of Bayes' theorem. So first of all, we talked about the prior probability, right? That's like prior knowledge. So the prior probability is our belief before observing any new evidence. So that's your state before you have additional evidence. For example, suppose only 2% of all emails are spam. So probability, so maybe from a record you read or from your own personal experience, you've discovered that out of 100 emails, two of them are spam. So probability spam is 0.02. So this probability is called the prior. So that's your base knowledge, so to speak, what you already had on ground. That's prior probability. And then that takes us to the idea of likelihood. Likelihood. So the likelihood measures the probability of observing the evidence, assuming that the hypothesis is actually true. So, for instance, for example, suppose that 95% of spam emails contain the word free. Okay. So, suppose that 95% of spam emails contain the word free. The probability that you have the word free, given that it's a spam, is 0.95. That is a likelihood like that. So, this tells us how likely the evidence is if the email is actually spam. That's likelihood. Next, we go for the evidence. So, for the evidence now, the evidence is the overall probability of observing the evidence regardless of the true class, no matter what is happening. So the evidence is the overall probability of observing the evidence, regardless of whatever the situation may be. For example, suppose 10% of all emails contain the word free. So let's say all the 10% of all emails contain the word free. So it means that probability free is 0.10. So the evidence serves as the normalization factor in Bayes' theorem. By the way, this is probability that you have the word free given that the email is spam. So it means this is only for spam emails, but the probability of free here tells you that, okay, if you have 100 emails, 10 of them contain the word free. That is your evidence. So the evidence serves as the normalization factor in Bayes' theorem. Now, we then have the posterior probability. So the posterior probability is our updated belief after observing evidence. For example, probability that the email is spam, given that it contains the word free, means probability that an email is spam, given that it contains the word free. Okay, I already said that here, but it's okay. Now I move on to intuition behind Bayes' theorem. What is the intuition behind Bayes' theorem? Bayes' theorem updates existing beliefs, right? So the process can be summarized as you have an old belief, you observe new evidence, and then you have to update your belief. So the stronger the evidence, the larger the change in our belief. So if you have strong evidence, you have a larger change in your belief. So let's look at an example. In medical diagnosis, suppose that 1% of people have a disease. So let's say of everybody you can ever think of, 1% of them have a disease. That means 1 over 100, that's 0.01. Then you now have a medical test correctly detecting the disease 99% of the times. So that's probability that the person tests positive, given that they actually have the disease, that's 0.99. So the test also produces false positives, that's 5% of the time. That's probability that the person is test positive, given that they do not have the disease. So that's 0.05. So if we now have to find probability that someone actually has the disease, given that they test positive, right? So that is where we have to compute we now have to go ahead and compute the evidence. So to compute the evidence, right, that's probability that the person tests positive. So what is probability that people that are tested test positive? So probability that somebody tests positive is actually probability that the person tests positive given that they have the disease multiplied by probability that they have the disease plus probability that they test positive given that they do not have the disease, multiplied by probability that they do not have the disease. So it's more like, this D is canceling this probability, this part is canceling this part. So it's more like a balancing act when you multiply by probability they have the disease and probability they don't have the disease. So since probability that they do not have the disease now is, so probability that people have the disease is 0.99. So probability they do not have the disease is now 1 minus PD, that's that's 1 minus 0.1. Sorry, probability that people someone has the only 10% of people have the disease, that's 0.01. So now, so you then have 1 minus 0.01, which is 0.99. So that's probability that people do not have the disease is 0.99 if you remove the 0.01 from 1. So we then obtain that probability that somebody tests positive, that will be equal to probability that they test positive given that they have the disease plus probability that they test positive given that they do not have the disease. So in that case, you have 0.0099 when you multiply this plus 0.05 times 0.99, that's 0.0495. So add everything together, you have 0.0594. So in that case, probability that someone tests positive is 0.0594. That's 5.94% of the times people test positive, whether they have the disease or not. Now that's the evidence there. Then we go ahead to talk about application of the Bayes theorem. So to apply the Bayes theorem, we now want to check probability that someone has the disease given that they test positive. So that means probability that that's probability that they test positive given that they have the disease. So that'll be like this first part now, 0.99 times 0.01 that we have up there, all over probability that they actually test positive. So if you check all of that out, you get 0.1667. Therefore, there's approximately a 16.7% probability that the patient actually has the disease after receiving a positive test result, right? So, I mean, this is actually low, right? So it means somebody testing positive is no guarantee that they actually have the disease. So, of course, you can set that up using Python. So if you set the prior to be 0.01 and the likelihood is 0.99 and the false positive is 0.05, the evidence now is the likelihood multiplied by the prior, all right, plus false positive multiplied by 1 minus the prior, just like what we had up there. Then the posterior now is likelihood times prior divided by evidence. And if you check that out, if you run this, you then get the evidence, like we computed, is 0.0594, and the prior, I mean the posterior rather, is 0.1667, as you can see here. So that is a case of medical diagnosis, applying Bayes theorem to medical diagnosis. So let's just go back to talk about the idea of spam email detection. So suppose that 40% of emails are spam. So that's probability that any email you get is spam is 0.40. That means that if you get 100 emails, 40 of them are spam. The 90% of spam emails contain the word free. So that means probability you have the word free given that the email is spam is 0.90. That's 90%. Then 20% of legitimate emails also contain the word free. So it means sometimes you also have legit emails that contain the word free. So probability the word free is there given that the email is not spam, that's 0.20. Then we now need to find probability that an email is spam given that it contains the word free. So first thing, we compute the evidence. So to compute the evidence, probability that the email contains the word free is actually probability that it contains the word free given that it's a spam multiplied by the probability that the email is spam plus probability that the email contains the word free given that it is not a spam multiply probability that the email contains the word free given that it is not spam multiplied by the probability that it is not spam in the first place. So since probability that it is not spam is 0.60, right? From what we computed from up there. So spam is 0.40. Not spam is 1 minus 0.40. That's why we have 0.60 here. So probability now that the email it contains the word free then is probability that of f given s, which is 0.9 up here, multiplied by it is spam, that's 0.4. Probability that it contains the word free, given that it is not a spam, is actually 0.20. Then probability that it is not spam is 0.60. So we have 0.9 times 0.4, which is 0.36. 0.2 times 0.6, that's 0.12. Add everything together, that's 0.48. So probability that the email contains the word free is 48%, is 0.4. That's 48 out of 100 emails contain the word free. Now, if you apply the Bayes theorem, then we have probability that an email is spam, given that it contains the word free, that means that the probability that it contains that is the probability that it contains the word free, given that it is a spam. That is this first part now. That's this 0.36 times 0.4 right there. And then multiplied by the probability that it is okay, this is 0.9 here. So yeah. So probability F given S. F given S, that's 0.90 as we have here, multiplied by probability of F. No, probability S rather. So you have that. That's 0.4. All over probability F. So you have 0.48. If you multiply that, you have 0.36 over 0.48, which is 75%, 0.75. So therefore, there is a 75% probability that the email is spam if it contains the word free. So, and we can implement that again. So you have probability spam 0.40, free, probability that it contains free given that it is spam, that's 0.90. Probability that it is free given it is legitimate, that's 0.20. And then you have your evidence, which is free given spam multiplied by spam plus free given legitimate multiplied by 1 minus spam. Then posterior is free given spam multiplied by spam over evidence. And if you compute all of that, of course, you get your evidence to be 0.48 and posterior is 0.75, just like we saw up there, like that. So, understanding the example now, suppose probability of B is 0.36 and probability B given A multiplied by PA is 0.36. So, applying Bayes' theorem now, we have that probability of A given B is equal to probability of B given A multiplied by probability of A, this, all over probability of B. So that is 1.00 in that case. So this means that every observed occurrence of B can be completely explained by a single event, by event A rather. So it means that A is all that determines B. That's basically what this is saying. So in practice, this situation is rare because multiple causes often produce the same evidence. So if you get one here, it means that probability that A will happen. So it means that as far as once B happens, A will always will most surely happen. So in that case, but that's always a rare thing in life. So in practice, this situation is rare because multiple causes often produce the same evidence. So we go ahead to talk about posterior. The posterior, of course, is useful evidence over total evidence. That's the posterior. So Bayes' theorem can be interpreted as posterior, which is useful evidence. So useful evidence is probability, is the evidence multiplied by the prior, all right? So useful evidence is evidence multiplied by prior divided by total evidence. So where useful evidence is evidence supporting the hypothesis and total evidence is evidence from all possible explanations. So like all possible explanation, that means if we use the case of okay, for probability A given B now, the total evidence is probability of B in all observations of what you are considering, like that. So we go on. So let's talk about Bayes' theorem in machine learning now. Many machine learning, we are looking at the equation behind spam filters, medical AI, and all of these things. And we see that that equation is Bayes' theorem because AI is all about, even generative AI, right? It's more like what is probability that the word after Paris will be France, something like that. So you now go ahead. So you see AI doing all this computation on so much data. So based on in machine learning now, many machine learning algorithms answer the following question. Given the observed features, which class is most probable? So examples include you have an observation, say email, and the prediction is whether it is spam or not. Symptoms, well, does it if you have a particular kind of symptom, does it mean you have the disease attached to that? Then the probability that an image is cat or dog, probability that a transaction is either fraud or legitimate, or even a speech is a spoken word or something. So Bayes' theorem provides a mathematical basis for making these predictions, and that is the place of Bayes' theorem in machine learning. And then we have the Naïve Bayes classifier, which is a machine learning algorithm. If you check my playlist on machine learning with EJD, you'll discover I talked about the Naive Bayes classifier, naive Bayes classifier. So the naive Bayes classifier assumes that all features are conditionally independent given the class. All right. So if the features are x1, x2 up to xn, then probability that C happens given that x had happened is directly proportional to probability of C and multiplication over probability, all the probabilities of xi's given that C had happened. So, although this independence assumption is often unrealistic, Naïve Bayes performs remarkably well for text classification tasks such as spam detection. Okay, so let's do an example of let's do an example code. So to 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 run this now from sklearn, that's scikit-learn, you want feature extraction, you want to extract text, and you are importing count vectorizer, and then from scikit-learn you are .naive Bayes, you are importing multinomial NB, that's naive Bayes, right? So imagine you have emails: win money now, cheap loans available, meeting tomorrow, project report attached. All right, and the labels, so each of these emails can be labeled as, let's say the first, this is spam, this is spam, the next one is not spam, the next one is not spam. I mean, win money now and cheap loans available sound like spam, right? Most likely. And then meeting tomorrow and project report attached sound real. Like, so those are not spam, not spam each. So you use so the vectorizer, now you bring it, you have the count vectorizer, and X, now you have the vectorizer that fits transform. So you transform these emails now, and then you now train it on the model, the naive Bayes model, to see if a particular email is actually going to be a spam or not. So imagine now that you already have these four emails, and you have established that the first two are spam and the last two are not spam, right? So by the time you train this model, you train your model with it on this data now and the labels. So model in 22, multinomial naive Bayes, and then you fit the model. So you have X, then labels, and then you now have a new email now. So you want to try now that, oh, if you see win free loans, what does that look like based on what you have seen over there? So if you do that, then the prediction, you have model.predict vectorizer the transform, then you're now taking the new email. And if you try to predict that, it gives you that is possibly spam, because win free loans sounds like what spams sound like based on the four cases we had. So imagine we say something like this. If I now change win-free loans to scholarship application, so I say scholarship application. So let's see. Let's classify. Yeah, this comes off as not spam based on what the model had seen from what spam and non-spam emails look like. So scholarship application does not look like spam, right? So those are cases. So let me take it. Okay, I'll copy this now, and then I take it back to what we had before. So win-free loans sounds more like a spam, while uh, uh, if I comment this out now, I have scholarship application. That sounds like not spam. So, and that's a very simple case of the naive Bayes classifier. Okay, so we go on to some real world applications. So Bayes theorem has applications across many fields. For instance, in email systems for spam detection, in healthcare for medical diagnosis, in banking for fraud detection, in cybersecurity for intrusion detection, for in robotics for robot localization, in artificial intelligence for classification, just like the one we did of the naive Bayes. Then for weather forecasting, for probability updates, for recommendation systems, you have personalized recommendations. Maybe maybe movie recommendations, restaurants to try out, or whatever it may be that may be recommended to you. And then we have advantages of the Bayes theorem, right? Provides a mathematically rigorous framework for updating beliefs. So Bayes theorem provides a mathematically rigorous framework for updating beliefs. So you can have a very scientific way of updating your beliefs instead of just assuming. Then it naturally incorporates prior knowledge, just like we know, and it handles uncertainty effectively. Then it performs well with incomplete information and computationally efficient for many classification tasks. Then it forms the basis of many machine learning algorithms, you know. Like I said, the whole idea of generative AI follows the whole this thing of having a prior, then having an evidence, and then at the end of the day, you can actually then you have a prior, you have a likelihood, and you have an evidence, and then you can have a posterior. You can update your what you know. So I mean, generative AI can then guess with a touch of assurance what the next word to generate is like. So in talking about the limitations now, of course, that the Bayes theorem requires reliable prior probabilities. So the probabilities have to be reliable. Then posterior probabilities depend on the quality of observed evidence, of course. So the evidence has to be reliable, then exact Bayesian inference can become computationally expensive for large models. So if you have large models, so that can become an issue. Then the independence assumption in Naive Bayes is often unrealistic. So that independence may not necessarily be true most of the time. So I mean, at fair level, it seems to work very well. Okay, so we can make do with that. So in summary, Bayes' theorem is a mathematical rule for updating probabilities whenever new evidence becomes available. So it combines prior knowledge, observed evidence, and likelihood to produce an updated probability called the posterior, right? So Bayesian reasoning forms the foundation of many modern intelligence systems, including spam filters, medical diagnosis systems, fraud detection software, recommendation system, and machine learning classifiers. And you notice that sometimes you have some emails that you don't see them that easily because they have been dragged into spam. So once in a while you get legitimate emails that go into spam, right? Because maybe they have characteristics resembling spam emails, right? But the most emails have been so developed that when any all these adverts that are not really important come, they just go into a spam filter, into a spam email. So you only see them by really wanting to see them. They don't come to distract you from the main emails that are legitimate. So understanding Bayes' theorem is an essential step toward mastering probability, statistics, data science, artificial intelligence, and machine learning. And then now we have our practice problems as usual. So as we have 20 of them, like we always have. So these are the 20 problems, and I'm going to solve two as usual. So in this case, I'll be solving problems 3 and 20. So I'll be solving this. A cybersecurity system flags 3% of network connections as malicious. So it correctly detects malicious connections 97% of the time and incorrectly flags normal connections 6% of the time. If a connection is flagged, what is the probability that it is actually malicious? So that we are looking for probability flagged given that it is malicious. Okay, we already know what the formula is going to look like. We'll get to talk about that soon. So apart from that, you can see the whole problems 1 to 6 right now. Okay, problems 1 to 6 all clear. Then you can see 7 to 13 all clear. 7 to 13. So I'm solving problems and 3 and 20. So this is 7 to 13. Then you have 14 to the end, 14 to 20. And the other problem I'll be solving is 20. A logistics company estimates that 65% of deliveries arrive on time. Customer satisfaction surveys show that 92% of on-time deliveries receive a positive rating, while 30% of late deliveries also receive a positive rating. So if a customer gives a positive rating, what is the probability that the delivery arrived on time? So that is positive given early arrival. That's what we need to look for. So let's go ahead and talk about this beautiful Bayes theorem that helps in medical diagnosis and all of that, and spam detection and all that. Okay, so let's go for problem 3 now. Problem 3. Oh, did I say problem 3? Oh, it's problem 4, sorry. Problem 4. Okay, let me check that again. Problem 4. Problem 4. A bank estimates that 1.5% of credit card transactions are fraudulent. So its fraud detection system detects 94% of fraudulent transactions, but falsely flags 3% of legitimate transactions. If a transaction is flagged, what is the probability that it is fraudulent? That is probability flagged given fraudulent. So we are solving 4 and 15, sorry, 4 and 15. So that's, oh, yeah, 4 and 15, 4 and 15. So 15 now is this. An airport security scanner correctly detects prohibited items with probability 99%. It falsely alarms on safe luggage 8% of the time. So if only 0.8% of passengers carry prohibited items and the scanner alarms, what is probability that prohibited items are actually present? Like that. So we have that problem 4 now. So I'll go for problem 4. So problem 4. So a bank, a bank estimates that 1.5% of credit card transactions, credit credit card transactions are fraudulent. 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 Its fraud detection system. Its fraud detection system detects 94%, 94% of fraudulent transactions. But falsely flags 3% of legitimate transactions. 3% of legitimate transactions. Okay. If a transaction is flagged, if a transaction is flagged, what is the probability? What is the probability that it is fraudulent? Okay. So we have to go ahead and first up in step one now, we define the event. Step one, define the events. Define the events. So here, let F be equal to transaction is fraudulent. Transaction is fraudulent. Then, so this is, okay, let me do this properly. This is kind of negation. Transaction is legitimate. Transaction is legitimate. Then A, transaction is flagged. Transaction is flagged. So here, probability that fraudulent is transaction is fraudulent. A bank estimates that 1.5% of credit card transactions are fraudulent. So a bank estimates that 1.5% of credit card transactions are fraudulent. So it means that probability fraudulent. So that tells us probability that the transaction is fraudulent is 1.5%. That is 1.5 over 100, which is 0.015. So that's its probability that the transaction is fraudulent. On the other hand, so it means if the probability that it is fraudulent is 0.015, so probability that it is not fraudulent would simply be 1 minus 0.015, which is 0.985. That's not fraudulent. So on the other hand, then we have that probability. So that means that probability that a transaction is probability that a transaction, probability A given F. That is probability that the transaction is flagged given that it's fraudulent. All right. Uh, okay. So its fraud detection system detects 94% of fraudulent transactions, but falsely flags 3% of legitimate transactions. So 94%. So if it is flagged, if it is fraudulent, that's 94%. So probability that it is flagged, even that it is fraudulent, that's 94%, which is 94 over 100, that is 0.94. On the other hand, so we have another part there that says that but it falsely flags 3% of legitimate transactions. So that means probability that it is flagged, even that it is not fraudulent. So probability that it is flagged, A is transaction is flagged, right? So probability that it is flagged, given that it is not fraudulent, is 3%. That's 3%, which is 3 over 100, and that is 0.03. So now uh we have to find probability that a transaction is fraudulent given that it is flagged. Okay? So probability that it is fraudulent given that it is flagged is what we need to get. Okay. So we have to find this, right? So that takes us to step two. So in step two, you have to compute the evidence. The evidence. Compute the evidence. And what does it mean to compute the evidence? So using the law of total probability, the law of total probability. So that means we check all scenarios using all the laws of total probability that what is A again now? Probability that a transaction is flagged, right? Is equal to probability that it is flagged given that it is fraudulent multiplied by the probability that it is fraudulent plus probability that it is flagged given that it is not fraudulent multiplied by the probability that it is not fraudulent. So that's total probability. So in this case now, that means we have a probability of A now. So A given F, we already have A given F up somewhere. That is 0.94. Okay, so this one now is 0.94. Then probability of F, that is 0.015. So 0.015 plus probability A given not F. Probability that it is flagged given that it is not fraudulent. That is 0.03. So this now we have 0.03 multiplied by probability that it is not fraudulent. Not fraudulent, that's 0.985 here. 0.985. So with that in place now, we then have, if you multiply this out, you get 0.0141 plus multiply this, you get 0.02955. So everything together is 0.04365. So that's probability that an email is actually flagged, whether it is fraudulent or not. So with that in place, we move on to step three. Step three, apply Bayes theorem. Apply Bayes theorem. So most of the work is already done with everything we've done before. So the probability that if a transaction is fraudulent rather, given that it is flagged. So that means probability that it is flagged. That's probability that it is flagged, given that it is probability that it is flagged, given that it is fraudulent, right? Multiplied by probability that it is fraudulent, all over probability that it is actually flagged, right? A is flagged, right? So with this in place, we can just fix up everything else. So probability that it is fraudulent, given that it is flagged, is equal to probability that it is flagged, given that it is fraudulent, and that's probability A given F, which is 0.94. 0.94. And probability flagged, like we already have also, is 0.015. So 0.015. And probability that it is flagged is that evidence we computed, that's 0.04365. 0.04365. So probability that it is flagged, given that probability that it is fraudulent, given that it is flagged now, is if you multiply and divide, you get 0.3230. Okay, that's the approximate value we have there. Okay, so what does that tell us? Um, therefore, therefore, even after even after the transaction, even after the transaction is flagged, even after the transaction is flagged, there is only there's only about 32.30% probability that it is actually fraudulent. Okay, so that's question 4 right there. Let's go on to question 15. That's problem 15. So for problem 15 now, we have this, that an airport, an airport security scanner correctly detects prohibited prohi prohibited items with probability 99%. It falsely it falsely alarms on safe luggage 8% of the time. If only 0.8% of passengers carry prohibited items and the scanner alarms, what is the probability? What is the probability that prohibited items are actually present? Okay, so we have that question 15 there. So let's go ahead and do this. So again, step one, you have to define the event. Define the events. So which events do we have here? First of all, you can let P be passenger. Passenger carries prohibited items. Passenger carries prohibited items. That's P. Of course, not P means passenger does not carry prohibited items. Passenger does not carry prohibited items. Prohibited items. Then A now, scanner gives an alarm. Scanner gives an alarm. Okay. So in that case, we are given the following. We are given that probability that passenger carries prohibited item. We saw it somewhere here. It's falsely. So if only 0.8% of passengers carry prohibited items, right? So that means we have 0.8% carry prohibited items. That's 0.8 over 100. That is 0.008 that carry prohibited items. So next we have, that means the probability that people do not carry prohibited items is equal to 1 minus 0.008, which is 0.992 there. Then of course, probability that probability A given P. Probability scanner gives alarm, given that there's no prohibited item. I think we saw that up there too. An airport security scanner correctly detects prohibited items probability 99%. So it gives an alarm and it is true. That is 99%. So probability A given P, that's 99%, right? 99%, 99%, that is 99 over 100. That is 0.99, like that. Then probability A given not P. Probability that the scanner gives an alarm without the item being prohibited. So if it falsely alarms on safe luggage, it's 8% of the times. So that means that 8%, which is 8 over 100, and that is equal to 0.08, like this. So it means that we need the probability that the item is prohibited given that the scanner gives an alarm. So this is what we need now. So what do? We go on to step 2, where we compute the evidence. Compute the evidence. So to compute the evidence, what do we have? So we have probability, the probability that the scanner gives an alarm, all right? And we need total probability. That's probability that the scanner gives an alarm, given that the item is prohibited, multiplied by the probability that it is actually prohibited, plus probability that the scanner gives an alarm, given that the item is not prohibited, multiplied by the probability that they are prohibited items, like this. So all of that will be A given P, we know that's 0.99. Then probability of P itself, that's 0.0808. So that's 0.99 multiplied by 0.008 plus probability A not given P, that's 0.992. So that is A not given P. Probability A not given P, that's 0.08. 0.08 multiplied by 0.992. So if you multiply this out, we get 0.0792 plus 0.07936. Put it all together, that's 0.08728. That's probability that the scanner gives an alarm. That's probability of A right there. So we have this. Then that takes us to step 3, where we talk about Bayes' theorem. That's step 3, where we apply Bayes' theorem. Apply Bayes' theorem. So apply Bayes' theorem. So that means probability P given A is equal to probability A given P, probability of P all over probability of A. So that means probability that the item is prohibited given that the scanner gives an alarm is equal to probability that the scanner gives an alarm given that the item is prohibited, multiplied by probability of prohibition that the item is prohibited by probability that the scanner gives an alarm. So that is 0.99 multiplied by 0.008, like we know. A given P already is 0.99. Then probability of P, we have that to be 0.008 up there, all over probability the scanner gives an alarm. That is the evidence we computed. That is 0.08728. 0.08728. 0.08728. Like this. So probability P given A now is equal to 0.0907. And that is the result we desire. So we can then say, therefore, even when the scanner, even when the scanner raises an alarm, even when the scanner raises an alarm, there is only about 9.07% probability that the passenger actually carries prohibited items. Of course, we get the percent by multiplying this by 100, right? So if you multiply by 100, that's 1, 2. That's why you get 9.07% here. Prohibited items there. Because prohibited items, because prohibited items are very rare, are very rare, relative, relative to the false alarm alarm rate. Okay, and with that, we are done with the idea of Bayes' theorem, which helps to, you know, in medical diagnosis, spam filters and things like that, and even in generative AI. So again, look at the questions. You can see 1 to 6 all together here. 1 to 6 there. I already solved I solved 4 and 15. So I solved 4 about bank estimates. Then you can see 7 to 13 or even 7 to 14 clearly here. 7 to 14 all together. And finally, you have you have the rest. You have every other thing. Let me know how helpful this is for you and if something and if there is something else you'd like me to talk about, let me know. Let me know how helpful this is. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to my channel already, I thank you very much for doing that. And if you have not subscribed, this is your time to do that. Why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges to find out when you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.